The first governing equation of fluid dynamics is the conservation of mass or continuity equation. This principle states that the mass can neither be created or destroyed, meaning that the net mass crossing a system must be balanced by either an accumulation or depletion of the mass in the system. This can be quickly seen if we take a look at the water passing through a water hose. What goes in on one side must come out from the other end. In case of compressible fluids, it is possible that the mass may increase or decrease in the control volume. So let's start and derive the conservation of mass in the Eulerian form. First, we start from the Lagrangian form where the mass variation is equal to 0. We apply the Reynolds transport theorem to transform the equation in the Eulerian framework. Then we can apply the divergence theorem to substitute the surface integral into a volume integral. The last step, we set the equation to be independent of the control volume. Since this integral is satisfied for an arbitrary volume, the integral has to be 0 to satisfy the equation. This leads to the final form of the conservation of mass in the Eulerian framework. The conservation of mass can be expressed in multiple forms. Here we are going to see the Cartesian form. If we substitute the divergence term into the Cartesian form, we get this expression for a three-dimensional field. Or we can simplify this into a 2D form, removing the component of the flow in the z direction. For incompressible flows, the density is assumed to be constant, so the equation of conservation of mass can be further simplified. If we assume constant density, we can reduce the equation to a simple relation that tells us that the divergence of velocity is equal to 0. This means that the volume does not change, meaning that the fluid volume entering our domain is equal to the volume that is exiting. This is why for incompressible flows we often state units of volume flow rate instead of mass flow rate. For example, we use liters per minute for pumps or cubic meters per second for fans. In this lesson, we analyzed how to derive the form of conservation of mass in its compressible and incompressible form. In the next lecture, we are going to see how to use a similar approach to obtain the conservation of momentum equation.